Hello everyone. So let me take you to one of the sample projects which I'm going to use for ETAP star mode. I have a system here with multiple source of contribution. I have a local generator supplying power and a utility which are feeding multiple motors. So we have some low voltage motors rated at 480 volt or 208 volt and some medium voltage motors rated at 4.16 kV. If I take you back to the top or upstream of the system, you can see that the generator and utility are connected through main breaker and some tie breakers between them. Based on the status or service of these main and tie breaker, we can have either one single source of contribution or multiple source of contribution. So let's see. I have set up some configurations here. I have configuration local, parallel or utility. So if I set the configuration to utility, my local generator breaker opens up and all the contribution is from the utility. But at the same time, if I set it up to parallel, the total current contribution is from both generator and utility, so a summation of both would be considered. At the same time, if I set it to local, we open up the utility breaker and the tie breaker and all the contribution is from the local generator. So what we are going to do is try to set up one protection scheme. We're going to see how we can protect our motors. Let's for example take motor IM12. So if I select the motor and rubber band all of the equipments protecting this motor and create a star view, I can see time current curve or star view of the protective devices and the element which needs to be protected. So to start with, I can play with the one line diagram of the elements which we have plotted. So I have this one line view and I can place it at any location in my star view, can zoom in to increase the size of all of these equipments or elements, or zoom out to a comfortable visualization level. You can see here we have two different kind of curves. First, curves related to the protective devices. So I have MCP curve or I have overload heater protective device curve. Second, we have starting and damage curves of the equipments. So I have a starting curve of the motor, right, and damage curve related to the stator of the motor and rotor of the motor. The rotor damage curve is basically the stall point of the motor. You can double click on any of these elements and open the associated editor to it, where you can see all of these settings. So I have thermal limit curve setting for hot start stall point or cold start stall point and stator damage curve. Once we have all the associated curve, we want to review the protection scheme. If you look at the MCP, you will find that the MCP is actually lying on top of the LRC section of the motor starting curve, which is an indication that if you try to start this motor with MCP in series, you won't be able to start the motor. Correct starting of the motor, the MCP need to be adjusted to one of a possible setting where it does not intersect with the motor starting curve. So if I set it to next higher or one step more higher, I can see there is enough gap between the motor starting curve and MCP for proper starting of the motor. But at the same time, I see I have overload heater curve too, right? So if I take a zoom window and look at this overload heater intersection, I can see these two curves are intersecting and probably overload heaters curve will not allow motor to accelerate to reach the full load capacity of the motor. Again, I need to play with the setting of this overload heater in such a way that it clears off the starting curve. So people using NEC knows that overload heaters are generally set up to 115% of the motor FLA. So if I look at the motor FLA, go to the motor editor, nameplate page, look at the FLA of the motor, I need to find a suitable setting for the overload heater. So let me open my calculator here and try to find out what will be 115% of 124 to get the proper setting of the overload heater. So 142.6 amps. So I open my overload heater editor and set it to 142.6 amps. Now you can visualize that by setting it correctly, the overload heater is not intersecting the starting curve, and it's also not intersecting any of the motor damage curves. Another important tool which helped me here to correctly view my one line star view is combination of these protective devices curve. So if you have two protective devices in series, you can combine them together to get accurate curvature of protection of this motor. We can also notice that the cable damage curve is protected as it's not intersected by the MCP. The last point of the MCP is cut off by the fault marker, and this fault marker is based on the maximum bus fault current for the protective device. It's based on the short circuit study ran inside the star mode. So if you are in the star mode and you select to run a new short circuit study, based on the standard selected, the short circuit current type selected, half cycle for maximum current and 30 cycle for the minimum current, and you update the short circuit, you will have your fault markers for the connected protective devices. Once protection is set up, the next important step is to verify the coordination or selectivity of the system. So if I go back to my one line diagram, for coordination and selectivity, I will need to place a fault on the system. So I select my fault insertion tool and place fault on the protected motor to observe the opening sequence of the protective devices up till my source. We can control the fault type and number of devices based on our study case. So if you go to the study case sequence of operation page, you can select the fault type and number of devices which need to be flashed. Irrespective of flashing devices, we can go to the sequence viewer to view operation of all the devices in the system. So here I can see my MCP for fault current of 37.248 kiloamps will start to open up in 1 millisecond and clear the fault in 15 milliseconds. Similarly, the next breaker will start to open up in 1 millisecond but will clear up in 24.4 millisecond. So for proper coordination, you need to observe the time gap between consecutive protective device operation. The sequence which we observed just right now is for three-phase maximum fault condition. But for a system to be properly set up, we will need to observe for different fault conditions. So what user can do, or what you can do, is go to the study case and select the correct conditions under which you want to fault the system or for which you want to study the system. So you can either select for maximum condition, maximum fault condition, that is half cycle condition, or minimum fault condition, which is 30 cycle condition. Also, you can either select the balanced three-phase fault, with asymmetrical RMS current or unbalanced line to ground, line to line or line to ground fault. So let me select one of these examples and set it to 30 cycle, which will automatically set fault type to symmetrical as it's a steady state and line to ground fault, and press OK. Once I set it to line to ground fault and set my report for prompt and again place a fault on this motor, with the report name, I can observe my sequence of operation is little different from last time. The CBTL11 has opened up faster than CBMCC1. So there is some kind of miscoordination between these two protective devices for minimum fault condition. Let's take another example and place fault on downstream of CBTL11 to observe coordination for transformer protective devices. So if I place fault on this bus and select these devices and create a star view, I can observe it's a different star view than my regular star view. This star view is called normalized star view or normalized TCC, which consider shift factors for these protective devices based on through fault current. One of the major advantage of doing this in ETAP is that fault can be placed at any location. So if I move my fault from downstream of the transformer, from downstream to upstream of the transformer, I can observe that the curves are shifted on the star view, as CBTL11 does not see any through fault current in this case. Because of the minimum fault current setup, it's not plotted and in the normalized view and correctly depicts the behavior of the protective device. I can go from normalized to my regular star view and see both the curves. But for normalized star view, as it's based on actual through fault condition, the CBTL11 curve is not shown on the normalized TCC view. Or if I go back to my study case and set it back to half cycle, press OK, and place fault on downstream of the transformer but upstream of the breaker, I can see a cross section between the relay curve and the low voltage breaker curve due to different shift factors. These shift factors can be observed from plot option preference page of the star view. So the shift factor for CBTL11 is 19.631 due to through fault current through CBTL11, whereas the shift factor for the relay is 1.875 because of the through fault current through the relay. So different shift factors for different protective devices based on actual fault condition will accurately depict the coordination between two protective devices. These examples showed how we can do protection and coordination in present release of ETAP. In future, ETAP is going to enhance the protection and coordination to a completely different level and make it much easier, much faster, and much convenient for the user. Let me show you a glimpse of what we are going to do in future release of ETAP. So I have a same system here, but I will use a different technique to do protection and coordination and analyze my results. The graphics just looks different because of the enhancements we have done in future release for ETAP. So if I select this motor and press the button what we call as star evaluation or AutoStar Evaluation, it will run an evaluation based on some rules which are predefined based on the rule book. So we have a rule book where you define the limits and kind of protection you're looking to run evaluation for. So once rule book is set up, you select the motor and run evaluation, which will run evaluation based on motor zone, protection zone, and the maximum through fault condition. So instead of taking engineering decision for motor protection, the software analyzes your system and tells you points of concern or points which are not correctly protected or coordinated by view of a visual display. So similar to our regular star view, we're going to set up the protection scheme. We're going to adjust this MCP in a manner that it recalculates the effect of MCP on the system. So as I adjust the MCP to a different setting, you can observe that issues have been cleared from the MCP, but we still have issues with the overload heater intersecting the starting curve, and that's what the software is telling you. The trip curve crosses the starting curve, and trip curve is too close to the LRC curve. So again, I play with the setting of the overload heater and correctly adjust to a level where it won't intersect with the curve, and software by view of result viewer tells you that your system is properly protected now. This product is under development and we can discuss more about it in future. At this moment, I will pass on to Steven to discuss sequence of operation for Arc Flash.
Hello, I'm Steven Chagoya, and welcome again to today's webinar. Today I will be introducing and presenting the Arc Flash sequence of operation, its functionalities, and applications for your project. So let's begin with the agenda. I will begin with an overview and background, then present the one-line view fault insertion, the Arc Flash sequence of operation viewer, and the Arc Flash sequence of operation from the Arc Flash report analyzer. So the Arc Flash sequence of operation has the same concept as the star sequence of operation, but with the main difference that the operation of the devices are determined based on the arcing fault current, as opposed to the bolted fault current. In many cases, coordination issues will arise because of the significant reduction in current during an arc flash event. This reduction becomes increasingly larger with low voltage systems, or voltages below 1 kV. So why and how can you use Arc Flash sequence of operation? Well, there are three main functions that this tool serves for the analysis of Arc Flash. Function 1 is that it can be used to simulate overcurrent protective device operation under changing fault currents, or also known as fault current decay. For example, systems with a lot of motor load or faults near the generator will experience a significant decay in current. As you may have already known, ETAP Arc Flash has three methodologies for the calculation of short circuit currents in the Arc Flash program. The two methods are half cycle, 1.5 to 4 cycle, both of these which are static currents or snapshots in time. The third method provides an approximation of the decay in the system short circuit currents near generators or large motors. If you go to the help file, as I have here up on the screen, under chapter 18, Arc Flash Analysis and Calculation Methodology, you will find detailed explanation for the determination of fault clearing times for these methods. The TCC curve that I have shown here highlights the example of the determination of fault clearing time using the 1.5 to 4 cycle method or the half cycle method. This plot currently shows the subtransient current for a half cycle calculation methodology. As you can see, the operation of CB23 will be based on the upper band of the instantaneous region. Similarly, CB22 will be evaluated the same way, but with of course that time delay. Now, when determining the fault clearing time based on the decay methodology, the program needs to consider the inverse characteristics of the protective device. This requires the integration over the three current values, which are calculated by this IEEE equation. In summary, when the X over R ratio is larger, for example at generator terminals, the decay in current will play a significant role in the actual response of the protective device. The following plot highlights this. If we were doing the analysis based on a static methodology, you would either find the response of the overcurrent device based on I2 or I1. But when analyzing based on the decay method, it will consider these three currents to find the actual time, which will have to consider the steady state current of the generator. So let's go ahead and show an example of this behavior in ETAP software using the arc flash sequence of operation tool. As you can see here on the one-line diagram, I have an isolated generator. Let's go ahead and place a fault on Gen bus 12.47 kV. As you can see here, the one-line diagram will display the arc flash boundary, the incident energy, and the fault clearing time. The sequence of operation will also show you the fault clearing time and the arcing current passing through the device at this time. If we open up the study case and go to the arc flash method page, you should see that this is being analyzed using the 1.5 to 4 cycle method. Now let's go ahead and set it to the fault current decay and see how this affects our study. As you can see on the one-line diagram, the results have changed significantly. The fault clearing time has increased to 1.272 seconds, and the incident energy has also increased because of that increase in time. The sequence of operation will now show CB21 flashing with that change in fault clearing time and the arcing current through the device at this time. You can also verify what current is passing through the device through the arc flash report analyzer. This one seems like it would be the steady state current, and that's what it is, as shown here under the source PDIA column. The second function that the sequence of operation can help with is to visualize the multiple source arc current contributions in your system. I'm going to go ahead and open another example to highlight this. This system here shows a looped type PD configuration for these three switch gears. I will go ahead and do a fault insertion here on bus B. As you can see, the operation of the devices are all operating to de-energize this fault. That is, those two fault current limiting devices on each end, and then that main circuit breaker. ETAP has an option for incident energy subtraction, and I'm going to go ahead and enable that just so that we can visually see the removal of contributions along with the sequence of operation. If I go to Tools, Options, Preferences, as I show here, the last option under Arc Flash is the subtraction of incident energy for multiple source systems. Let's go ahead and enable this and press OK. I will go ahead and rerun another Arc Flash fault insertion here on bus B, and you will see the removal of that incident energy for the final incident energy calculation. So it has reduced at about 4 cals when considering the removal through these two tiebreakers, which is about almost 10 kA of contribute together. So this visually highlights what's going on in your system during an arc flash event. The third function that the arc flash sequence of operations serves is to identify areas with potential coordination issues, which arise from the nature of this arc fault. If I go ahead and navigate to another portion in this project, I'll go ahead and explain this condition. So here we have a low voltage 480 volt MCC bus. We'll go ahead and run an arc flash analysis, the classical method of just running the triangle with an arc flash. So the results are shown and the device is operating at 135 milliseconds. Everything seems okay. Let's go ahead and confirm the operation of the device by running a sequence of operation. Now, as shown on the one-line diagram flashing of devices, you can see that it's uncoordinated, or you're not being selective enough by clearing the MCC first. So now load A breaker is operating first, and then that main switchgear breaker, and then finally the main MCC at 2.62 seconds. Of course, the first device, which is the load A breaker, is the one to de-energize completely the fault. And that is reflected with the incident energy and the fault clearing time results shown here on this bus, 0.135 seconds. Now, this current that is passing through the device is approximately 8.5 to 8.8 seconds. Let's generate a TCC curve of this portion. Using the crosshair, I'm going to go ahead and mark my 8.5 current, which is somewhere around here. And you can see that the coordination shown on the sequence of operation fault insertion reflects that of the coordination here on the TCC. So what we can do to fix this is lower the short time pickup of this low voltage breaker for the MCC main, and also increase that relay pickup so that we can have some selectivity in our coordination. And now we can simply rerun the study under arc flash. Now the coordination looks better. You see MCC main operating first at 130 milliseconds. 5 milliseconds later, load A breaker, and then finally the main switchboard. Of course, the results are determined based on this main operating device at 130 milliseconds. The purpose of the upstream devices flashing are just to show you what will occur in an event that that main does not operate, what your next line of defense would be. And in this case, it would be load A breaker. So let's go through some of the functions and settings of this feature, or the arc flash sequence of operation feature. The arc flash sequence of operation will use your current setup, your current ETAP setup. So that is, it's going to calculate based on your current revision, your current configuration, and whatever you have set in your arc flash study case. So there is no other special settings that you have to play with when running a sequence of operation. It'll just take what you have. Now there's certain locations that you can fault, and these correspond to an arc flash analysis. You can fault the MCC bus, or just buses, line side of your equipment, the load side, and then finally motor terminals, or the motor terminal enclosures. And furthermore, you're going to see that the one-line diagram, the icon for the sequence of operation fault insertion, will actually highlight yellow, indicating that you can execute the sequence of operation event. Again, the one-line diagram, or the flashing, will display the fault clearing time and the arcing current at that time. One other feature that you can have for the arc flash sequence of operation is control over the flashing of the events. So you can either increase the speed of the flashing or pause it altogether. You can do so by entering the display options on the right hand side toolbar and locating the arc flash sequence of operation section here at the bottom. You have a maximum of 3 flashes and a minimum of 0, which means pause. So let's go ahead and show you 1 flash per device. And we can go ahead and pause it. Sometimes your eye doesn't want to see any flashing, and it's much better to analyze just showing paused sequence of operation. There is another setting for the arc flash sequence of operation, which is the modes of operation, or the amount of flashing during a sequence. This setting is enabled through the Tools Options preference. Under the arc flash section, there is an option titled Sequence of Op, Report PDs that de-energize each source path. Currently I have it set to false, and as shown on the one-line diagram. When it's set to false, it first shows you the first device to operate. For this case, this is a radial system, so then it's going to show you the next line of defense or the next operation of devices following first operation of your device. If I were to set this to true, you will only see one operation because you're only telling the program to display the first device to de-energize, completely de-energize your fault. Now notice that the upstream devices are no longer flashing. And we could go ahead and show this with the other system with multiple source contributions. Now notice that the CB1 and CB4 on the other switchgear mains will not operate. So your fault current limiters are the ones to go first, and then finally your main protective device for bus B. Okay, so now realistically when you're working on your project, you're not going to be doing fault insertions for every case. Typically what you have set up are scenarios, and you use a report analyzer to identify any problematic areas. So I'm going to go ahead and switch to another project. Now in this system I have cogeneration and various differentials set up. So let's go ahead and execute this scenario and open up the arc flash result analyzer. As you can see here on my report analyzer, I have 2 locations which are color coded black. I have set this up to identify which locations have fault clearing time not determined. Let's go ahead and further filter these locations out by using my filter results by option, and it will be the first one called FCT not determined. Now my analyzer is indicating to me all the locations in which the fault clearing time cannot be determined. Now the usefulness of this sequence of operation is that you can launch it after you've already executed your scenarios without having to execute it from the one-line diagram. The options are shown here: sequence of operation, viewer, and the one-line diagram fault insertion. Let's go ahead and select 101 sec and launch the sequence of operation. As shown here on my one-line diagram, I receive an FCT not determined message and then the operation of these devices. Notice that the branch that the generator is feeding is not being de-energized. In ETAP, the generator will be sustained at steady state, and it's required for it to be de-energized in order to fully find the fault clearing time. You can also see and inspect that there's only differential set up and no overcurrent device here in this first level to de-energize it. Similarly, N1 is the same case, so we can launch this viewer. Now the ArcFlash sequence of operation viewer provides to you a tabulated report of the one-line animation. You can grab as many buses as you wish by simply clicking on the first row, shift, and the final row, and enabling the ArcFlash viewer and simply launching it. This here will provide to you the full sequence of events and give you the final condition. So for 101 secondary on this switch gear, you see here that the arc fault will not de-energize. Now let's go to a different fault location with a different KV. And you see here that the operation for this tertiary transformer 1 will be 476 breaker and 576 breaker. And these of course are transformer differentials, and the arc fault has been de-energized. Now the great thing about this tool is that you can export it to Excel and have a list of the operation of your devices for this project, and you can then also troubleshoot some of the fault clearing times not determined. I'm going to go ahead and close this one and now run a wizard that I have set up with 4 different cases. Now let's go ahead and launch the ArcFlash Report Analyzer. I have here configured my ArcFlash Report Analyzer to show my incident energy worst case for my NFPA 2070-2012. And I'm going to go ahead and launch the sequence of operation for my 101 secondary and figure out why my fault clearing time is at 45 cycles and an energy of 50.63 cals per centimeter square. Let's move this to the side. Now, as you can see here on the one-line diagram, I do have a fault clearing time determination, but my relay 16 differential is not operating 101. Furthermore, if I were to actually launch the viewer, I can see what actual relays are operating. And it is shown here that 576 is being tripped by differential relay A, and downstream relay 2 is operating circuit breaker 1-2. Now none of those being the relay 16. So now I know that there's something wrong or something has been configured with my relay 16 incorrectly. So I'm going to double click it, and I notice right away in my info page that my condition is set to out of service. So if I were to put this back into service, I should expect my differential zone operating. And as you can see, the differential relay 16 zone is now de-energizing this fault well below 100 milliseconds, and you can see that change in incident energy. And of course, by launching the ArcFlash viewer, you can also see this. Now finally, you can also view single phase sequence of operation events, but this can currently only be done through the ArcFlash Report Analyzer. What I'm going to do is go ahead and launch it, and I actually have my ArcFlash single phase case in here, bus 6 and bus 7, and I can go ahead exact same way as in 3-phase analysis, launch my viewer and as well as my fault insertion. Okay, so this concludes the ArcFlash sequence of operation portion of this webinar, and thanks again.